The Food and Agriculture Organization of the United Nations estimates that around 1/3 of all food produced for human consumption in the world is lost or wasted each year. The disposal of food waste to landfills is not sustainable as it leads to rapid depletion of finite landfill space and imposes a severe burden on the environment. This project developed a novel bioprocess which makes use of food waste for the sustainable production of polylactic acid fiber. The material is applicable to the textile industry. The process consists of three main steps: lactic acid fermentation, lactic acid polymerization, and polylactic acid melt spinning. To utilize food waste as fermentation feedstock, two specific fungi are added to the waste. Enzymes are actively secreted in situ by the fungi through solid-state fermentation. The solid enzyme-rich fungal mashes are then thoroughly blended with the food waste and undergo hydrolysis in a bioreactor. This process hydrolyzes the waste, producing a nutrient-rich fermentation feedstock. Bacteria consume the nutrient in the feedstock, producing lactic acid during the fermentation. In order to recover the lactic acid from the fermentation broth, it is necessary to remove cell biomass and colored impurities. First, the broth is filtrated and centrifuged to remove cell biomass. Second, colored impurities are absorbed by being mixed with activated carbon. The next step in the process involves the solution being concentrated by rotary evaporation. This is followed by continuous extraction of the solution using ethyl acetate via sonication. The resultant solution is separated with organic phase in separatory funnel. Finally, lactic acid is isolated from the ethyl acetate by distillation at 40 degrees Celsius for 30 minutes. This process demonstrates that the lactic acid recovered from the fermentation broth is polymerized into polymer PLA through ring-opening polymerization. The research applies a novel catalytic method with zinc oxide nanoparticle dispersion as the catalyst in lactide synthesis. The lactide is synthesized by dehydration, oligomerization, and depolymerization. The lactide is then purified by recrystallization in ethyl acetate, and the precipitate is separated by vacuum filtration and then dried in a vacuum oven. Following lactide purification, the PLA is synthesized by ring-opening polymerization by heating the lactide at 200 degrees Celsius for 25 minutes under nitrogen. The last step involves purifying the PLA by precipitation in cold methanol. The precipitate is separated by vacuum filtration and is then allowed to dry in a vacuum oven. This procedure produces high-purity PLA with a relatively heavy molecular weight. The PLA obtained can be manufactured into fiber through melt spinning and can thus play a significant role in textile production. As the PLA is biodegradable, the final textile products can be degraded ultimately into H2O and CO2 in a natural environment. In this way, a sustainable PLA life cycle is created.